Hello, everyone. I hope you are having a wonderful evening. I want to talk to you a little bit today about rate of change. Um, but before we get started on rate of change, I know we've talked a lot about it throughout the year. I want to give you a moment right now to think about anything that you know about rate of change. Write down everything you can think of about rate of change, um, and then we'll go from there. Cool. So I'm sure you came up with a lot of things having to do with rate of change. Um, but the big thing that we are focusing on with rate of change is that it is a change in y compared to a change in x. And we've called that delta y over delta x. And there might be a lot of other things that you wrote down. You might write down things like rate of change is the same thing as slope. That's a good one to write down. Or that m is the variable we use to describe slope. You might have written down something like rise over run. Maybe you wrote rise over run down there. And I'm sure that there's a lot of other things that you may have been able to come up with. The big one that we're really going to be focusing on for the remainder of this lesson is we're going to be looking at that delta y over delta x. And we're going to kind of jump into some problems, some different situations where we can use that delta y over delta x. So let's take a look. So we're going to look at this. We're being asked to find the rate of change for the hours traveled and miles traveled, and then interpret what it means. So we're trying to find a rate of change on this graph. And I think the easiest way for us to do that, again, is to consider delta y over delta x. That's absolutely what we're going to be working with here. And in this particular case, because we're looking at a graph, the way that we will measure delta y most likely is as some kind of rise on the graph, and the way we can measure delta x is with some kind of run on the graph. So as you're looking at this graph, I'm going to find my first intersection point, which is happening right there. That's a nice intersection. It's a nice clean intersection between two lines here. I have this line and this line intersecting right there at that dot. I have another one here, and there's one here, and there's one here. And because this line is linear, that rate of change is constant. It should be the same rate of change between each of those dots. Therefore, it shouldn't matter which dots I pick. One thing we want to consider when we're looking for rise and run is we want to consider the units on the y-axis and on the x-axis, and we want to consider what they're counting by. So you might kind of mistakenly think that this is a rise by 1 and a run of 2. But the reality is here, this rise of 1 box really represents a change of 60 miles. We're rising by 60 miles. And our run units are really just counting by 1. So this really is, from 2 to 4, is a change in 2 units. Therefore, we are rising 60 and running 2. And if we would like to go ahead and simplify that, our rate of change will become 30 over 1. If we want to think about what that represents, what 30 over 1 represents, it's going to represent 30, whatever my y unit was, and the y unit was miles, so 30 miles per hour. 30 miles per hour is what's being represented there. All right, so let's take a look at another example, and I want you to try to figure this out now. I'd like you to determine the slope of this line using the idea of rise over run. Go ahead. Cool. So looking at rise over run, in order to get from one point to the next intersection point, guys, I got to tell you, this is an intersection point right here. I know that there's a point all the way over here, but we don't have to go all the way over there. We can find any good intersection points, and there actually are quite a few on this graph. And we can rise up 1 and over 2. My slope becomes, or my rate of change becomes 1 over 2, delta y over delta x. Rise over run. If we did go ahead and pick that furthest point, notice that it's going to cause us to rise by 1, 2, 3 and run by 1, 2, 3, 4, 5, 6. That would give us a rate of change 3 over 6. Well, a rate of change 3 over 6 is exactly the same as 1 over 2. 1 over 2 is just a little bit more simplified. All right, let's try one more like this. I'm going to ask you to find the rate of change on this graph right here. And again, it's a little bit difficult to see the lines here, but I think you can make out where some good intersection points are. Go ahead and give this a try. Cool. So I think one really good point for us to go with might be something like the y-intercept, and the next one is the very next intersection point. That would work. We could continue to find some other points. So maybe you chose this one, or maybe you chose this one, or even this one. Whichever one you chose, because this is linear, picking any 2 points here should work for us. So my rise is going to be, I'm going up by $4. I'm rising $4. And again, we're looking at these numbers. It's going from 4 to 8, which is a change of 4. And then we're going to come over by 5 miles. So my rate of change is going to be 4 over 5. And if we wanted to talk about what this represents, it represents $4. These units are all in dollars. $4 per mile. The taxi charges $4 for every 5 miles that the taxi goes. Cool. So let's apply this concept now to situations that don't necessarily involve graphs. We're not going to use rise and run. We're going to be looking at numbers instead. So I'm asking here, is this relationship linear? Is this relationship linear? And in order to determine if it's linear, I have to figure out, does it have a constant rate of change? Does it have a constant rate of change? And if I want to figure out if it has a constant rate of change, I have to check the rate of change between every point. So we're going to give ourselves an x variable and a y variable, an input and an output. And we're going to check our delta y over delta x. So on this first one, delta y is 15, while delta x is 1, 15 over 1. And the next one, delta y is 15, and delta x is 1. And the next one, delta y is 15, and delta x is 1. And finally, 15 for delta y, and 1 for delta x. The slope all the way down the line, 15 over 1, 15 over 1, 15 over 1, 15 over 1, suggests that this does in fact have a constant rate of change. And because it has a constant rate of change, the relationship is in fact linear. Is this relationship linear? Absolutely, yes, it is, because it has a constant rate of change. So I want you to try this now. I would like you to determine whether or not this relationship, the relationship on the page I'm showing you now, the relationship between number of hours and the charge of the babysitter, is this a linear relationship? If so, why do you think so? Cool. So, yeah, the answer is yes. By now you know whether you're right or wrong. It is a linear relationship. If we go ahead and look at the rate of change here, we're going to get a delta y of 8 over a delta x of 1, a delta y of 8 over a delta x of 1, and a delta y of 8 over a delta x of 1. The rate of change here is constant. It is 8 over 1, and this is, in fact, linear. Cool. Last thing for us to take a look at. The last thing I want to take a look at in terms of linear functions here is I want us to determine the slope between 2 points. And when we go to do that, it's much like we did previously on a table, except we don't have a table. We're given just 2 points. So we're going to create our own little table. I want us to find the slope of the line that goes through the points negative 5, 3, and 2, 1. Why don't I give you a second to try to do that right now? Go ahead and try to do that. Okay, so let's see how we should have set this up. We should have created a real quick little XY chart, right? And on that XY chart is going to go negative 5, 3, and 2, 1. And from there, I need to find my delta y. My delta y is going to be from 3 to 1. How do I get from 3 to 1? And the answer is I have to go down by 2 units. And then how do I get from negative 5 to 2? Well, the answer from negative 5 to 2, that's going up. So that's an increase. And from negative 5 to 2 turns out to be an increase of 7. Think about that for a minute. If I start at negative 5 and I need to end at 2, there's a 0 in the middle there. From negative 5 back to 0 is going up by 5 units, and from 0 to 2 is another 2 units. Therefore, this is changing by plus 7, and that's my delta x. So overall, my slope is going to be delta y over delta x, which is, going to be negative 2 over 7. Negative 2 over 7 for my rate of change here. Cool. So that's it for finding the slope of linear functions. I have one little bonus question that I want to throw in here, and that is that sometimes we talk about rate of change in nonlinear questions. And we don't tend to want to talk about rate of change here, but we have this concept of something called an average rate of change. And that just means that even though we know it's not linear, if it was, what would the slope be? So here, they're asking us to use the graph of this function. So we have this function on the right, and they ask us to use this graph to figure out the average rate of change from x equals negative 3 to x equals negative 2. Well, where x is negative 3 on this picture is right about here. And where x is negative 2 on this picture is right about here. And if I'm trying to get from that point right there to that point right there, I'm going to need to do some rising and some running. So when I count rise and run, I always want to go from left to right. So this is my furthest left point, and that's my furthest right point. So that's going to be my starting point and my ending point. To get from the start to the end, I'm going to go down, and then I'm going to go over. But the question is, how much should I go down and how much should I go over? And there's a little bit of a tricky scale on here that's a little bit tough to read. But this is indicating 2, and then down here is 0. And it seems like they're counting here. Every 2 boxes counts as 1. So I went from a y value of 2 down to a y value of negative 1 here. That means that this went down, even though it counts like 1, 2, 3, 4, 5, 6 boxes, it was actually only 3 units. So we'll write a 3 there. And because I'm going down, I'm going to write a negative 3. This is a decreasing slope here. It's going down. And then we're going to go over by 2 units, but each of those units is really only a half. I actually only went over by 1. And since I'm going to the right, it's positive. Therefore, my average rate of change is going to be negative 3 over 1. That will be my average rate of change from that point to that point. It basically is saying, if I connected this with a straight line segment, what would the slope of that line segment be? And it would be negative 3 over 1. All right, so this video has gone on long enough. I'm going to go ahead and leave you now with that review, and hopefully you're able to apply that in class tomorrow as we continue to work. All right, have a great rest of your evening. Take care, and see you soon.